j. So if you use tau, which is a more obvious way to describe a Riemann surface of genus 1, you have to worry about modular invariance. But if you change variables from tau to j, then modular invariance disappears. The modular invariance information that's contained in tau is no more, no less than the value of j. It's actually slightly more convenient to subtract the constant and let capital J be this function. So, I mean, in the 19th century, this function was constructed, and it was a little bit funny that the coefficients are so big. This one was just a historical artifact. You can change it by subtracting a constant. But you start with this problem that doesn't involve big numbers, which is to eliminate the action of the modular group on tau by changing variables to a new variable that contains all the modular invariant information. Let me finish what I'm saying, and then you can interrupt. So the question doesn't involve any big numbers, right? But the answer involves big numbers. It's a little bit like the gauge hierarchy problem. The answer involves a big number, which is the ratio of the Gutt scale or the Planck scale to the W boson mass. But we don't know what's the question that hopefully doesn't have a big number, that has an answer that involves a big number. So here, the question was to solve for modular invariance by introducing a modular invariant variable. No big numbers there. But when you solve the problem, out pop big numbers. Forget this one, which can be changed. But this one, we can't modify. J was unique up to adding a constant. So this 196884 is just a fact of life. And the coefficient after it is something like 2 times 10 to the 7. And they grow from there. So big number, it's like this, well, I won't repeat the analogy, but there was a question. If you show your test now.
I'm just wondering why have you focused specifically on this one?
Because it's easier. But knowing genus 1 is equivalent to finding the energy levels, but not knowing the interactions. So it's not a complete description of the theory, but diagonalizing the Hamiltonian is a good start. So modular invariance means that the partition function is a function of J. We could say it's a modular invariant function of tau, but it's much easier to say it's a function of J. Now, the partition function actually has a pole at Q equals 0 because the ground state has negative energy. Even our approximate partition function had a pole at Q equals 0. But there are not supposed to be any other poles because in general, in conformal field theory, the partition function converges as long as Q isn't 0. So the only pole is at Q equals 0, which means J equals infinity. So a function of J that's only infinite when J is infinite is otherwise known as a polynomial in J. So the partition function must be, with our assumptions, a polynomial in J. Our assumptions might be wrong, but they lead to the conclusion that the partition function is a polynomial in J. And we can be much more specific. It must be a polynomial in J of order k, because since the ground state energy was minus k, the pole at Q equals 0 is of order k. Right? Inside the sitter space has energy minus k, and the excitations above it have less negative energy. So the pole is of order k, and therefore the partition function is a polynomial in J of order k. So it's determined by k plus 1 coefficients a sub r. It can be written like this. And we can solve for all the energy levels if we're given k plus 1 numbers a sub r. I told you that homomorphic factorization was a drastic simplification, and here it is. We can find all the energy levels of multiplicities in terms of k plus 1 unknown numbers. Now we can, for example, we can pick these coefficients to make z of q agree with the naive function up to and including the term of order q to the 0. They are precisely k plus 1 coefficients between q to the minus k and q to the 0. And if we ask to get this function up to terms that vanish at q equals 0, then the A's are uniquely determined. And since they're uniquely determined, we have no control over the term of order Q. It's above the ground state by K plus 1 units, so there will be primary fields of dimension K plus 1. Well, we interpret them as black holes since the theory is trivial except for the black holes. In fact, something nice happens. The minimum classical black hole mass in these units is K. But the Bekenstein-Hawking entropy vanishes if the mass is precisely K, so classically black holes of positive entropy exist precisely if the mass is greater than K, which is in perfect accord with the fact that, according to our proposal, the lowest dimension of a primary other than the identity is K plus 1. We didn't put in the minimum mass of a black hole, but we kind of got it out with a little sleight of hand. And the partition function that I've described how to calculate, though I didn't really write down a formula, gives a result for black hole degeneracies that agrees perfectly with the Bekenstein-Hawking entropy. This may sound like a miracle, but it wouldn't be if you're familiar with the fairy tale of Dicraft, Montesano, Moore, and Verundi. Just for fun, if K is 1, the partition function is the J function itself, and the number of states at mass level 2 is therefore 196884, and one of them is the stress tensor, or I should say one state corresponds to an operator, which is the stress tensor. So the other 196883 states are primaries of dimension 2. And the black hole entropy is therefore the logarithm of 196883, which is 12.19 approximately, while the classical entropy of a black hole with K equals 1 and mass 2 is 4 pi, which is about 12.57. So we're only off by a little bit, and it gets better from there. If you increase K and the black hole mass, it quickly improves. After all, this is the case that is worst. The Bekenstein-Hawking approximation that we use here is an approximation when the radius of curvature and the black hole Schwarzschild radius are both much bigger than the Planck length. But by taking K and the mass to be as small as possible, we've gone as far as possible from the classical limit. So this is really the worst we're going to do, and it will only get better from there as we approach the classical limit. But let's go back to K equals 1. The number 196883 is a very special number. Back in the 70s, the last of the sporadic or exceptional finite simple groups was constructed, the so-called monster. The lowest dimension of an irreducible representation of the monster is 196883. It was John Mackay who noticed that this is very close to the coefficient of the third term in that 19th century function, the J function. And soon it was discovered that higher coefficients of the J function are similarly related to the monster. And Frank, Lopowski, and Merman constructed, well, first conjectured and then constructed, a holomorphic conformal field theory whose partition function is our friend capital J. They also conjectured that their theory is the unique holomorphic CFT with this partition function. If that's right, and if holomorphic factorization is also correct, then the Frankel-Lopowski-Merman monster theory must be the right one at K equals 1. Well, if C equals 24 or K equals 1 is a valid value for quantum gravity, and if holomorphic factorization holds, that second one is a big if, perhaps, then the Frankel-Lopowski-Merman theory must be the right one. So we can interpret the monster group